Hey everyone, we're back for our third lecture on the heart. Last time we met, we went over, we were introduced to the four phases of the cardiac cycle. Remember, cardiac cycle is everything the heart is doing within one heartbeat. And first phase we're going to discuss is ventricular filling. Like the word filling tells me that volume is increasing. So blood is going into our ventricles, and we can talk about the two ventricles. We can just talk about the left, because whatever's going on the left is going on the right, okay? So the left ventricular volume is increasing. This means the entrance door, which is the mitral valve, has to be open. Now, if blood is going in, blood is going from left atrium down to left ventricle. Therefore, pressure must be higher in the atrium, because blood always goes from where pressure is high to where pressure is low. Now, pressure is low in the ventricle because the ventricle is going to be in diastole. Now, also, our entrance door is open. Therefore, our exit door must be closed. So our aortic semilunar valve has got to be closed here. Now, it's actually closed because left ventricle pressure is low, which is because it's in diastole, and left ventricle pressure is lower than aortic pressure. So blood that's up here is trying to go backwards because of that pressure difference, but it cannot do it. So that's what's going on with volumes, valves, and pressures in our ventricular filling phase. Now, we do have to make one point really quick here. Most of ventricular filling, like the first 80%, is utterly passive. The last 20% is active, meaning the atria are contracting. So the last fifth or so of this phase, in terms of the volume being moved, is going to be due to atrial contraction. Now, at the end of filling, the amount of blood in the ventricle, at the end of filling, that is known as the end diastolic volume, okay? So at the end of filling, the ventricle is also going to be done relaxing. So we're at the end of relaxation, we're at the end of filling, and the amount there is going to be the end diastolic volume. Okay, cool. If we look at a graph, notice that during this phase, look at two graphs here actually, let's do this one on the left first. During this phase, we got volume on the Y, we got time on the X, and volume is going up. Not like crazy, but it's going up, 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 up. Then it does take a little jump here. Right here, where you see the little change, like right here, that's when the atria start contracting. And we're getting our last bits of blood down into the ventricle. And we're achieving that end diastolic volume. So in this case, the end diastolic volume of our ventricle is 130 mils. And of course, the volumes are going to be this, they're going to average the same. So if it's 130 on the left, it's going to be 130 on the right. Now, meanwhile, we can look at the pressures. Notice that left atrial pressure is greater than left ventricle pressure. That's why blood was going into the ventricle. That's why it was filling. Because it's flowing from the atrium to the ventricle. Atrial pressure is less than ventricular pressure. This difference is why the mitral valve is open. Now, meanwhile, look how high the aortic pressure is. Much higher than ventricular pressure. That's why the aortic semilunar valve is closed. All right, excellent. And with that, we are done our first phase. Let's move on to our next phase, which is isovolumetric contraction. So obviously the ventricle is going to be squeezing here. Iso means the same, so same volume. So this name will become really obviously apparent in a moment. All right, so we're done filling. The ventricle starts contracting. As the ventricle contracts, the pressure in here starts to rise. Almost immediately, pressure in the ventricle becomes greater than the atrium, and so blood tries to go back upward. Blood tries to go upward. What does blood do? It shuts this valve here. And the shutting of the mitral and the tricuspid valve creates the first heart sound. The first heart sound is the lub sound. When you hear the lub-dub of the heart, the first heart sound is the lub sound. And it's created by the AV valves shutting. The AV valves are shutting because blood's trying to go backwards. Blood's trying to go backwards because pressure here is now greater than pressure up in the atrium. And that is because the ventricle has started squeezing. However, aortic pressure, the pressure up here in the aorta, is still really high. So the ventricle has not generated enough pressure yet to open this guy. So the ventricle created enough pressure to shut this one, but not enough pressure to open this one. So both valves are closed. And that, folks, is a crucial thing. Both valves are closed, okay? If both valves are closed, no blood's going in, no blood's going out. The volume of the ventricle is not changing, hence isovolumetric contraction. And these valves are both closed because ventricle pressure was greater than atrial, because the ventricles have started squeezing, but ventricle pressure is still below aortic. The ventricle has not generated enough pressure yet. So what I want to do now is add on to my earlier graphs. So earlier we had ventricular filling going on here, but now the volume is staying the same for a period of time. This period of time where the volume stays the same, and the volume is nice and high here, it's at the EDV, the end diastolic volume, this is isovolumetric contraction. Now meanwhile, remember, contraction, the ventricle is in systole, it's squeezing. Therefore, its pressure is rising. Notice how during this period of time, ventricular pressure overtakes atrial right here. That's what makes the mitral valve slam shut. But the ventricle pressure has yet to exceed aortic pressure. So the aortic semilunar valve is still closed. Okay, good. We're now on to number 3 in our phases. Our third phase is ventricular ejection. The ventricle is still squeezing, so left ventricle pressure is still going up, and now it's gone up enough to open this valve, the aortic semilunar valve. So now ventricle pressure, like left ventricle pressure in this case, exceeds aortic pressure. And because it exceeds aortic pressure, this valve, the aortic semilunar valve, gets pushed open and blood moves from ventricle to aorta. Thus, the ventricular volume is going to go down because blood is being ejected. Now, meanwhile, the mitral valve is still closed because this pressure is really high, this pressure is really low. Although notice that blood is being received by the atrium. Blood is coming back from the lungs still, going into the atrium. So blood's starting to fill up over here. All right. Very good. Very good. Let's move on. And let's introduce a new term. The amount that leaves is called the stroke volume. So the amount ejected is called the stroke volume. The amount ejected, whoopsie, the amount ejected is the stroke volume. Now it's important to realize the ventricle does not squeeze out all of its blood. It doesn't empty itself. And the amount left over is called the end systolic volume. So the amount when the ventricle is done squeezing, end contraction, end systole, is going to be the end systolic volume. The amount ejected is called the stroke volume. Stroke volume, by definition, volume ejected by a ventricle per cardiac cycle. Notice it says by a ventricle. So the right ventricle will have its stroke volume, and the left ventricle will have its. And of course, they should balance out. They should be equal on average. Now, mathematically, we can figure out stroke volume by taking the end diastolic volume, the amount before contraction, the amount before you squeeze, and then subtract the amount left over, the amount after you squeeze. So EDV minus ESV is going to give you your stroke volume. Now, a good thing to think about is, or actually we'll get to our thinking question in a second. Let's do our graphs first. So here is isovolumetric contraction. So right at this point, right here, this point is when the aortic semilunar valve opened up. So blood in the ventricle, the volume there starts to decline. This point is where the aortic semilunar valve is going to close. I didn't draw that perfectly. This point is where it's going to close, okay? And volume is going down because the ventricle is ejecting blood. The amount, like the difference between the before and the after, is called the stroke volume. So figure out your stroke volume in this case. How much blood was ejected by the ventricle in this example? Figure that out. Stop me. Next time you see me, tell me the answer. Just shout out the answer at me. Okay? All right. Let's keep on going. And let's talk about another important consideration. What we got to consider is why we had that leftover volume. All right, why we didn't eject the entire EDV. Why there was a leftover amount called the end systolic volume, which in my graph was about 70 milliliters here. Why did we leave so much? Well, here's the thing. Right now, like, what are you doing? Maybe you're sitting down watching this. You don't want to pump out 100% of your blood from your heart, because what if you need to pump out more? What if you were in, what if this little cute doggy came by and you got a little scared and you needed to run away? All right, if you were pumping all of your blood out with every beat, like at rest, then you would have no reserve left over to pump out in times of need. All right, so that's why we don't eject the entire end systolic volume and diastolic volume. Okay, if I look at my pressure graph for ventricular ejection, notice that ventricle pressure is greater than aortic. Ventricle pressure is greater than aortic. That's why that aortic semilunar valve is open, and that's the exit door. Remember, that's the exit door, which is why blood was able to leave. All right. Let's keep on going. We've got one final phase before it all repeats itself. The final phase is isovolumetric relaxation. The left ventricle relaxes. It starts doing diastole. Contraction is done. Pressure in the ventricle starts to drop. Almost immediately, pressure in the ventricle becomes lower than aortic. So almost immediately, aortic pressure up here is now greater than left ventricle pressure down here. So blood tries to go backwards. It cannot get in there, but it does push this valve shut. And the shutting of the two semilunar valves creates the dup sound, which is the second heart sound. However, pressure in this ventricle is still more than pressure in the atria, in this atrium, even though the atrium is filling up with blood coming from the lungs. So this mitral valve has yet to open. So again, isovolumetric, notice that both sets of valves are going to be closed. All right, so mitral valve shut because left ventricle pressure is higher than left atrium. Aortic valve shut because left ventricle pressure is lower than aortic. So no blood going in, no blood going out. Volume is not changing. Isovolumetric. And if we look at our volume graph, notice that it is a straight line right here. Now eventually, at this point right here, atrial pressure is now going to again be greater than ventricle pressure. The mitral valve will open at this point, and notice that the volume has started to rise here because we're going to start filling again. Okay, magnificent. And by the way, this is where the aortic semilunar valve closed. So aortic closed here, mitral opened here. Between this period, all my valves are closed, so I got a straight line for volume, isovolumetric. All right. Now, in my pressure graph, we're relaxing, right? So pressure is falling. Notice how quickly it falls below aorta because aorta is so high, and it continues to fall and fall and fall. But during this period of isovolumetric relaxation, ventricle pressure is dropping, but it is still above atrial. And then once it drops below atrial, that's when we're going to start our next phase, which is ventricular filling. Back to the beginning, because of course it is a cycle. All right, I got a series of questions here I want you to do. We'll do these in our regular lecture class too, but if you do them beforehand, awesome. Don't wait for me to do things for you. Figure this stuff out. Use your brain. Train that brain. And let's introduce a new thing we can measure and talk about. This is something called cardiac output. It's the volume of blood pumped by one ventricle in 1 minute. So again, the left and right will each have their own cardiac output. And of course, they're going to be the same on average. Mathematically, cardiac output is heart rate times stroke volume. Realize that heart rate was beats per minute, right? And if you multiply that by stroke volume was milliliters per beat. And what's going to happen to my beats here? My beats are going to cancel out. And I'm going to be left over with milliliters per minute, which of course I could convert to liters per minute if I so desired. So cardiac output right there, it's what it is. That's how we figure it out. And cardiac output has got to be balanced. Got another math problem here for you to do. Use your calculator if you need to. Do this. Notice I underlined, bolded, and changed the color of one word. That's probably an important word. Tell me what you get when you see me. All right, so if the ventricles pump different amounts of blood per minute, in other words, if they have different cardiac outputs, so like for example, if the right ventricle cardiac output exceeds the left, well, pressure and fluid will back up and build up in the lungs, and that's bad. On the opposite situation, if the left ventricle's cardiac output exceeds the right, pressure and fluid are going to back up and build up and accumulate in systemic tissue. I don't want either of these to happen. I do not want my lungs to fill up with fluid, of course. All right. In that discussion of the cardiac cycle, we learned about stroke volume and cardiac output. Let's talk about some regulation. When we regulate stroke volume, the number one thing is this concept called preload. It is the most important. the major thing that's going to regulate and determine stroke volume, something called preload. Other things that can affect stroke volume but don't have the same degree of influence include something called contractility and something called afterload. Okay, let's talk about what all three of these are, starting with preload. Preload refers to the degree of ventricular stretch. Well, what stretches the ventricles? Well, blood. In other words, preload refers to the amount of blood in the ventricles when it's full. And the amount of blood in the ventricles when it's full is the end diastolic volume. And this is so impactful because there's something called the Frank-Starling law. The more the muscle stretches in the heart, the better the overlap between actin and myosin. So the more the heart stretches, the better the overlap between actin and myosin, and the more efficient the contraction. So as volume goes up, as end diastolic volume goes up, I don't just want to say volume there, as end diastolic volume goes up, stroke volume goes up as well. This is called the Frank-Starling law of the heart. Whatever goes in goes out. So if more blood comes in, the heart stretches more, better overlap between actin and myosin, and it squeezes better and it ejects more. If less goes in, less goes out because there's less stretch. So, if more blood returns to the heart, ventricular stretch increases, better overlap between myosin and actin, more tension in the ventricles, and more blood gets ejected. All right, that's the Frank-Starling law of the heart. Easy way to remember is whatever goes in, goes out. Okay. Contractility refers to how hard the ventricle is squeezing, regardless of its level of stretch. If you squeeze harder, like if you have an increase in contractility, if you squeeze harder, stroke volume is going to go up. Norepinephrine and epinephrine are sympathetic fight or flight system chemicals. Increase contractility. They make the ventricle squeeze harder. So, think about it. You squeeze a tube of toothpaste harder, more is going to come out, right? That's the idea here. Squeeze harder, more comes out. During exercise, you release these guys on your heart, and your muscle in your heart squeezes harder. You're going to pump more out. So preload was how much is coming back in, and whatever goes in goes out. Contractility is how hard our walls are squeezing. Now, afterload is the pressure the ventricle here, the left ventricle, has to overcome in order to open the semilunar valve and eject blood. So in order for this valve to open, the left ventricle has to generate greater pressure than what's in the aorta. And another way of talking about that pressure is to call it afterload. So, suppose aortic pressure up here in the aorta is high. The ventricle is going to have to expend more energy opening this valve, and it'll have less energy, and less time too, with which to eject blood. Therefore, the amount ejected would decrease, the stroke volume would go down. Now, under normal conditions, this one, afterload, is not a problem. If we have some sort of heart failure and other things, then afterload can negatively impact that stroke volume. If aortic blood pressure goes really high, the heart will respond, the left ventricle will respond by getting thicker and thicker and thicker in order to overcome it, to overcome that afterload. This is actually not a good thing. We don't want this thick wall. It is hard to keep the cells here fed and oxygenated as they grow thicker and thicker. All right, I got 4 questions for you to do. Again, do these. Come talk to me. Let me know what you got. Let me know your reasoning. All right, last thing I want to talk about, among the last things, are what exercise does. Exercise is so essential for proper cardiac health. Exercise is so good for your cardiovascular system, for your heart. Exercise, especially, aerobic exercise, endurance training, whatever that might be for you, running, walking, bicycling, swimming, whatever you got, it is going to make your left ventricle's contractility, your ability to squeeze with power and force is going to increase. The chamber size of the left ventricle will increase. So your heart can accommodate more blood. It can fill up with more blood. And if more can go in, again, remember Frank Starling law, more can go out. Endurance training also increases the coronary circulation. Like, you will have a more diverse array of blood vessels. You will grow new blood vessels, new branches. And that is an excellent thing. So do what you like to do. Walk, run, bike, get on the machine. Who cares what it is? Do what you like to do. Exercise. Okay. Fantastic. This is a heart with a bad situation. Can you look at this and figure out what the bad situation is? Can you find the problem here? And can you tell me why it is so bad? Again, hit me with that in class or in wherever you see me. Grab me and stop me. Be like, hey, M. Holtz. And then tell me what your answer is. And this is how we fixed it. Not we, but this is how it got fixed, by the way. So see if you can figure out what they did here to fix the problem. All right, another picture. This is a problem called mitral stenosis. What happened to our valve opening here? Here's the tricuspid valve opening. What happened to the mitral valve opening? And why is that so bad? Look at the two openings and tell me why that is so bad, okay? Giving you lots of things to talk to me about, so come talk to me. And we are done lecture number 3, part number 3 of the heart. And we did it in less than half an hour, which that is just amazing on your part. Good job. Hopefully you sat through this whole thing. If you took breaks, that is cool. Do some rewatching, some re-listening, take some more notes. Come see me, study. And I'll catch you in the next video I do. Bye-bye.